Okay, so we are doing optimization problems. So when you think of an optimization problem, think about a parabola. It may not be a parabola, but think of a parabola. And when you want to think of like maximum like income or something like that, well, that maximum, like let's say this is time, let's say this is money. Well, your maximum income occurs at this time, and this is your maximum income. So it occurs at the vertex. You see that? No. But it also occurs, um, the vertex is the place where your derivative is equal to zero, where the horizontal tangent, where the tangent to the curve is horizontal. That's where the maximum is going to occur. Okay, so that's something to think about. Um, but another thing to think about also is you also want to double check your endpoints. So let's say income was like you're asking about like year 5 to year 30, and year 5 you switched careers. Year 5 was an awesome year, and then it was like bam, like that, and then like that, and then whatever, like that. Things just went really bad. And then if you do your horizontal tangent, you're gonna get, if you find your derivative equal to zero, you're gonna find that. You're also gonna find that, right? So you want to find which one is the maximum, and you're like, ah, I found that maximum income. There it is. It's that amount, whatever that number is, that corresponds to this year right here, right? And you're that is your answer, and you're wrong because you forgot to plug in your endpoints. If you would have plugged in 5 into the original equation, you would have found that actually year 5, which didn't even involve any calculus to figure out, was the higher number. So over that year span, you also want to plug in your endpoints. So it looks like if I did this a little bit better, that year 30 would have been like an absolute min, right? If this value is lower than that, like that value, or even that value, even though it doesn't look like it, if it was like closer down there. So you always want to plug in those endpoints. Can't stress that enough because I used to forget to do that. So frustrating to do all this calculus and think you have yourself your awesome answer, and then you forget like you're supposed to just plug in the endpoints, and then you find like there's a better answer. Exactly. So that's the whole point of like finding the absolute mins, and versus the local. And sometimes the locals are the absolutes, but sometimes the absolutes from the outside are just the absolutes, like the ones, just the endpoints. Okay, so this problem here, a box with a square base and open top. All right, so I'm gonna draw my box. Okay, so it's a square base and open top. Must have a volume of 32,000 centimeters cubed. All right, so we know its volume, V equals 32,000 centimeters cubed. And we know it's a square base, so we know that that's x and that's x. Like whatever the length is, the width has to be also. Find the dimensions of the box that minimizes the amount of material used. Oh, okay. So amount of material, that's kind of like the same thing as saying amount of wrapping paper minus the lid. Like how much wrapping paper, what's the area of the wrapping paper minus the lid? Does that make sense? Well, it has no, it says here, it has an open top, right? So it doesn't have, it's like a, you know, it's like a box that filled with toys, no lid on it. Okay, so they want to know the material, like how much wood was used or how much cardboard was used. Well, that's the same thing as saying like, how much wrapping paper do I need to wrap this box with no lid, right? So, okay, so amount of material, that's a surface area question. That's that's surface area minus the lid. So that's the surface area without the lid. Okay. Okay. So, but then they say here, then they give us the volume of this thing, right? So we know that the volume equals length length times width times height, which is equal to 32,000 centimeters. Centimeters cubed. Okay. Um, so, but we know that the length and the width are the same thing, right? So V, because they're with X, right? So is X times H, which is equal to 32,000 centimeters cubed. All right, so V equals X squared times H, and that equals 32,000. So I can go ahead and get rid of my V right here because it's equal to 32,000. And if I wanted to, I could actually I could actually solve for H. Right, so I could divide both sides by H squared. I'm sorry, by H. Just kidding. I could divide by X squared. We'll just edit that part out of the video. Divide that, bam, and we have H equals 32,000 divided by X squared. So now I have H in terms of X. Okay, let's put that on hold for a second. So surface area, what's the surface area equation? Well, let me think about this for a second. Um, you could invent your own surface area equation, which is just add up all the pieces. But there's an actual surface area equation. So if you have like a prism, let's draw it like this, rectangular prism, and you open it up. All right, so it's like a piece of paper. Like, let's say you fold it up. So don't think of it as a box. Think of it as a piece of paper that's been folded up to look like a rectangular prism. So it has a hole in the bottom and has a hole in the top. You follow me? Okay, so if I had a piece of paper, I could make it look like this. I could fold it and I could make it look like this. These are holes. So my paper, so if I open up my paper, I mean, okay, so if I open up my paper, you would have four sides to it. It would look like this. There's my paper. And I'm going to go ahead and color. Yeah, I think so. Go ahead and color. Go ahead and draw it. And if you haven't colored it yet, I would not do these colors right here, just the ones on the bottom. Oops. Ooh, you should color it. Bam. It's okay. Wait. Don't mind me. Okay. All right, here we go. So then I'm going to get my colors here. I'm going to go yellow, pink, blue, and green. So do you see how, oh, and then I'll get some weird color, like some color that's different, like orange, and put orange right here, and I'll put orange right here. So do you see how my opened up piece of paper corresponds to the prism, the rectangular prism, right? So you have the width, which is the orange piece, and then the yellow plus the pink plus the blue plus the green is actually the perimeter of the base. Do you see that? All right. So well, we know that length times width is area, right? This is like length, this is width. So I can get the area of all of this business by multiplying length times width. So to get what's called the lateral area, to get the perimeter of all the sides, okay, you want to get your surface area. So you want to get your perimeter of the base times your height. So lateral area equals perimeter of the base which is the color lengths, times your height. Okay, so, well, no problem. In our example here, our perimeter of our base is x, actually. I mean, our each color is x, right? So this is x, 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 x. So it's x. So this is x. This is x, right? That's x. It's x. So it's x plus x plus x plus x. It's 4x. So 4x times our height. Well, our height, this is about no, they're both kind of related. They just look differently. Yeah, but so you can think of this box, you can think of this box as being this box. You can think about them both being the same. Correct. Because the 4x has to do with the actual problem. It's just whenever I think of prisms, I always just think of them as being taller. Okay. You with me? Okay, so we know that the base is 4x. The perimeter of the base is 4x. Times the height, well, we'll just call that h for now. We'll put it over here. We'll call that h for now, right? Okay. So we have our lateral area. Our lateral area, or LA, is 4xh, right? Okay, and our, what's it called? Our base, oh, and then you need surface, yeah, we have h. Wait, our surface area though, or sorry, our base area. So surface area equals lateral area plus base area plus base area if you were going to do like the top. But we're not going to do the top. We have an open top, right? So we don't need this. We don't need this one because of the open top. So, and we know that the base area is x times x, right? So I'll put it right there, x times x. So our surface area equals 4xh plus x times x. Then, well, that's the same thing as, so surface area equals 4x, and you're right. We know what h is in terms of x. 32,000 over x squared. 32,000 over x squared plus x squared, because that's what x times x is, right? Okay. Then our surface area minus the bit lid on top is, we can simplify this, right? Bam, bam, and you have an x on the bottom. So you're going to get a 4. I really hate how I wrote this. Hold on. It looks like a times. Okay, so we have that. So we have, what'd you say? 4 what? Oh, I'll do the next step. 32,000 over x plus x squared. Okay. Okay, so 32,000 times 4 is 128,000. So surface area equals 128,000 over x. Now I'm going to do it differently. I'm going to write it as, no, I'll just do it like this. 180,000 over x plus x squared. So this is the formula that gives me the surface area, right? So so I could have like a box that's like this, like crazy tiny little box, and like this, right? And I say like, oh, I want this to be like 1 inch. I want my x to be 1 inch. That's 1 inch, and that's 1 inch. That's a 1. Okay, then this formula will tell me in inches how much wrapping paper I'm going to need, right? It could be anything. I could have 5 inches there, or 5 feet, or 5 miles. What's that? Yeah, if I want to know how much wrapping paper I needed for my 1 inch silly example, but it's got to satisfy the criteria of having a volume of 32,000 centimeters cubed, right? So it's going to be a very tall box because it still has to satisfy that criteria. Okay, so let's erase this for a second. Okay, so this is some sort of graph. I don't know what this graph looks like. We could graph it. I'm not going to. But I know that I could write this a different way. I can write this as S for, I'll write it as A actually. A, area, A, as a function of X. Area as a function of X is equal to 128,000 times X to the negative 1. Because we're not crazy people. We're not going to quotient rule this thing. Plus X squared. Okay. So this is the same graph. I didn't do anything. Let's just pretend that this graph looks like this. Doesn't, but let's pretend it does. Well, how are we going to find that maximum value? No, you said negative b over 2a. We're in calculus. Yeah, we're taking the derivative, we're going to set it equal to 0, and we're going to see where it has a trough or a crest, where it has a valley or a hump. Okay? But I forgot something. Back up to the original problem here. it says, yeah, I forgot about this. So the volume is 32,000, right? So you kind of have to think of a domain. So what is our domain? No, domain means what can X be? So okay, wait. So a domain? No, it's like a real world domain. So we know that the volume is, we know that this is the same thing. We know, like, can we draw it again? We know that no matter what, this is X and this is X, you know, and this is our height. So we know that X has to be greater than 0. We know that for sure. You can't really have a box. You can have a box that has a dimension of 0 on the sides, but but you could have a box that has a dimension of 0.0000001 on the sides, right? Um, and let me think about this. Okay, you ready? All right. So there's something I said that was kind of wrong. So, well, actually, maybe I didn't even mention it yet, but the the side length, the smallest possible side length is 0. It's kind of a really weird thing to think about, but it's always going to be 0. Like you can have no side, like no like length and width at the base. Yeah, so it's always going to be like that. Okay, so x is greater than or equal to 0, and you can have, so it's basically a square bottom with that has a, that has 0 length and width. Okay. Yeah. Yeah, no problem. It's like having a square bottom with 0 length and width. Doesn't really make sense to me, to be honest with you. It would make more sense if it was greater than 0, because at least you'd have something. But the fact that you have nothing, to me, is kind of weird. But that's how you do it. Okay. All right. So then as far as the maximum, but they're all done this way, and then the maximum the x can be. Well, we know that length we know that length times width times height is 3200, right? So the most x can be the most x can be is is the square root of 3200. Yeah, hold on a sec. Okay, so what's weird about this problem is that x can be anything. Okay, so normally they're not always like that. Like if you have like so much like fencing material, there's only so much x you can use. But for this particular problem, you can mess with your combinations to always get a volume of 32,000. Okay, so h can be a fraction. H can be some sort of fraction, x can be something else, and you can always get like you can always like you can always get 32,000. So your domain is greater than or equal to 0. That's it, actually. Runs all the way to infinity. And I watched a video, and a guy was like, oh, the way I think of it is the domain is greater than 0. That's how I think of it too. But in the textbooks, they say greater than or equal to 0, so that you can have a 0, like x is just like run down to nothing. Okay? So the official way is x is greater than or equal to 0. That's it. That's your domain for this problem. Done. Okay? So go over here, and we take our derivative. Okay, so we're going to take our derivative. So we have a prime of x equals what? Okay, negative 120,000 x to negative 2 plus 2x. Okay, so that's our derivative. So if you want to find out where max and min's, what are you going to do? Set equals 0. So you're going to have negative 128,000 times x to the negative 2 plus 2x equals 0. And then I'm just going to rewrite this completely as over x squared. Or here, let's just do it like this. Let's just do it like that. So negative 128,000 over x squared, because that's what x negative 2 is, plus 2x equals 0. Okay, so now how do we solve for x? Let's do that. What happens if you do that? So let's multiply by x squared. I don't know. Let's try it. Multiply by x squared over 1. And multiply by x squared. Oh, by the way, you know how we said like x is, actually never mind. So multiply by x squared. All right, so if we did that, we would get negative 128,000 plus 2x equals 0. Yeah, it's always weird to wipe your x's out like that, you know? But that's the only like logical move. So let's keep going. Plus 128,000 plus 128,000. And you have 2x 128,000 divided by 2 divided by 2. What's 128,000 divided by 2? X is equal to, I just had my assistant check that. It's correct. Okay. So 64,000. Got that? So what the hell does that mean? What does that mean in this problem? Well, why not? Yeah, that's true. It because it that's kind of a weird number. Not if actually, not necessarily. So yeah, so let's keep going. you said this little sketch of a number, right? But the reason why it's kind of weird is because what if the height is a fraction? It's a whole other level. That'll bring your volume back down again, right? So even though you get some monster base, if you got some fractional height, which is why your domain can be infinite, because like there's all these possibilities. Okay, so let's go ahead and we're gonna do our sine graph, okay? Because what we did was we found a number. We actually didn't discover if we found the maximum length or the minimum length. Maybe we don't know if we actually maximized, I said that wrong. We don't know if we maximized surface area, if we minimized it. All we know is we got a horizontal tangent there. Okay? So let's go ahead and put our 64,000 there. And let's go ahead and plug in an x to the left and an x to the right into our derivative. I guess you can do that. Can you do that? I don't know about that. Don't plug in 0. No, plug in 1. What happened to 1? Or, yeah, plug in 1. You can plug in 1. Okay. So we have a prime of 1. Hold on 1 second. Okay, let me use the restroom real quick. Okay, so we're plugging in 1, right? Okay, so, well, if we're plugging in 1 to the derivative right here, that's an easy one, right? Yeah, so you have, it's just negative 128,000 dun, 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 over down below 1 squared plus 2 times 1. So it's negative 120,000 plus 2, so it's negative. Okay, so negative means decreasing. Okay, so decreasing. Well, that's kind of interesting. So then we go over here and we plug in 65,000, right? All right, let me bring our derivative right here. I'm going to do a prime of 65,000. Okay. So a prime of 65,000 is, I'll just erase that, make this over 65,000 squared plus 65,000. 2 times 65,000, right? 2 times 65,000. Okay, and that seems like, I don't know what that is actually. So you have 120, so you have 65,000 squared, just do it over here. So 65,000, so 65,000 to the power of 2 gives me that. So I'm going to go negative 128,000 divided by that last answer is that plus 2 times 65,000, which is positive 130,000. Okay, so this positive, bam. So negative, positive. We know we have a minimum. Let's go back to this problem. This problem is saying find the dimensions of the box that minimize the amount of material used. Okay, so we know that 64,000 produces a minimum. So we go to our surface area formula, and because that's the amount of material we need, right? And surface area formula, the one that has no h's in there, is this one down below right here, right? So, is that right? Yeah. Is that right? Yeah. So go here. So we have area, or surface area, is equal to that, and then in place of x, we're going to plug in 65,000. Okay, so then we have 128,000 divided by 65,000 plus 65,000 to the power of 2. That's a crazy number. Did you get that number? That number just seems really wrong. So we're saying, so find the dimensions. We're not asking for the surface area. We figured out the surface area. We found the surface area that minimizes the box. That's not what they want actually. They want the dimensions of the box. Find the dimensions of the box. Okay? So we know that we have this box. Here it is. Where you have these two things that are exactly the same. This x, and we have this h. And we know that the volume, we know that x times h is equal to 32,000. And we know the x value. The x value that minimizes the box is 64,000. Actually, first of all, was that number was wrong, that 65,000 number to begin with. Yeah, it should have been this number, right? It should have been that number. So we want to use, okay, so hold on, let me erase this. This is gone. Actually. Okay. So we know that 64,000 is the value of x that minimizes the volume, right? Or the surface area. 64,000 is the value of x that minimizes. This is the minimum of the surface area formula. Okay, and we know that we also have a volume equation. We know that volume, according to our square bottom base box, is x times h, which is equal to 32,000. Okay, so we know that volume equals x squared times h, which is equal to 32,000. Okay, but now we also know the value of x that minimizes this volume. We know that x is 64,000, right? So we can go here, 64,000 squared times some unknown height equals 32,000. Now we can just solve. So take our calculator, go over here, 32,000 divided by 64,000. We're isolating h. Divided by 64,000 squared is that crazy number there. Huh. Don't like that. So h is equal to 7.8125 times 10 to the negative 6. And this just seems completely wrong. Hold on. Found the mistake. So we multiplied both sides of the equation by x squared. Or did we? Because this wasn't multiplied by x squared. So you have to hit everything. So that was my bad. I didn't notice that. Like, even though you said it, it sounded good. Well, not really. All the hard thinking is done and done. So let's go over here. This is gone. Look, that's not actually a lot at all, actually. It's so you're over here. Okay, so here we are. You multiply x squared. You have to hit everything. I think it's a good punch in the face, actually. So make sure not to do that again. Make negative 128,000 plus 2x cubed equals 0. Okay. So now we have plus 128,000 plus 128,000. So you have 2x cubed equals 128,000. Divided by 2. Divided by 2. X cubed equals 128,000. Yeah, that's right, 64,000. 64,000. Then let's go ahead and raise that 64,000 to the power of 1/3. To the power of 1/3. 4,000, you say. 40. So, close. One, 1/3. That's why I don't trust my mental math. Your number would have made sense to me. Okay, x equals, what did we say it was? 40? Okay, cool. So new sign chart, slightly lower than the last sign chart. We have 40 right here. And we're going to go ahead and plug something to the left, something to the right of our derivative. So we can plug in 1, right? And we know that if we plug in 1, what's going to happen? It's negative. So, right, so if you plug in, let's just do it. A prime of 1 equals, let me put this down here. Okay, so A prime of 1. So equals negative 128,000, and then x to the power of negative 2 is really just x downstairs, x squared downstairs, so that's 1 squared plus 2 times 1, which is negative. Okay, negative. Bam. Now we're going to go ahead and plug in, be lazy, and plug in, wait, that's right. We're going to plug in 41. All right, so A prime of 41, put a 4 right there, 4 right there. So we're plugging in 41 into our derivative. Okay, and then we have negative 120,000, 1, 2, 3, divided by 41 squared. Bam. And then you're going to do plus 2 times 41. And then we get 5.85, which is positive. So, all right. So we've established we have a minimum. And that minimum happens where? It has at 40. So you go over here and you say, all right, well, I need to know my dimensions of my box that occur at my minimum. So you say, well, I know the volume of the box. The volume, like the dimensions that give me that volume, which was length times width times height, which was 32,000, right? Okay, so we know that x squared times height is 32,000, and we know that we know our minimizing x is 40. So 40 squared times height is 32,000. Okay, divided by 40 squared, gone, divided by 40 squared. Okay, so 32,000, 32, 1, 2, 3, divided by 40 to the power of 2. I don't know why I did it, it's 20. So h is 20. Minimizing height is 20. So we know our dimensions. What is it asking for? Find the dimensions of the box that minimizes the amount of material used. All right, well, I say that we have it's going to be say it again. Yeah, so length equals that's not a 40, equals 40, what are we on, centimeters? What is this? This is centimeters. So length is 40 centimeters, length of the base is 40 centimeters, width is 40 centimeters, and height is 20 centimeters. And we could double check that at least that gives us our 32,000. So base area, 40 times 40, times our height, 32,000. Okay, so 40, 40, 20. Hold on one second. And then normally you'd want to plug in your endpoints, but you're not going to plug in your domain. The domain was from 0 to infinity, right? And yeah, so just leave it like this. It's good. We're done. Yeah.